All right, welcome everyone. So today we will be finishing up chapter 13. Before we do that, I'll just do a couple of quick announcements and also see if there are any questions before we get going. Let's see here. So some announcements, right? So there'll be a quiz on chapter 13. We'll have it kind of like a 24-hour window roughly between Friday and Saturday to do that quiz. Now the quizzes take like, I think you have like a 20-minute, 15-minute time. That's how long you would typically get in class if I was giving these quizzes in class, and I designed the quizzes to be the same type of quiz I would give in class. And so, within a 24-hour window, you should be able to find, 15, 20 minutes to take the quiz on Canvas, right? And note that 2 weeks from now is our first exam, okay? If you're coming in on Wednesdays, you'll have the exam on the 23rd. If you're coming in on Monday, you'll have the exam on the 28th. Okay. While I will not be giving the exact same exam between Wednesday and Monday, I'd still prefer those who've taken the exam on Wednesday to not talk to other people about the exam, right? For those that on Monday to have an unfair advantage, right? That only hurts yourself if you're taking the exam on Wednesday, tend to give people on Monday a better advantage and, raise the curve or something like that, right? So you're kind of screwing yourself over. So I highly suggest not sharing exam information, but I'm also not going to give the exact same exam because I'm not an idiot. I will have a quiz on chapter 14 before that exam because we should finish up chapter 14 by the 21st. So there'll be a quiz kind of that Monday, Tuesday period for exam 1 on Wednesday. Okay. So kind of a quiz here and a quiz here. Okay. Right. Again, on these quizzes, right, you're working by yourself. Shouldn't be using any outside information besides what's provided on the quiz. On exams, you will be given information that's given on this sheet here. There's a version of this on Canvas, okay? Right? And this is the only information, extra information you are allowed to have on the exam, whether you're in class or taking the exam via Zoom, okay? So these are the only equations that are provided, right? And you'll be given a periodic table and, a bunch of constants and conversions and such if needed, right? Right, reminder for those who are doing the exam on Zoom, you'll have to sign in to take the exam either Wednesday or Monday during regular class time. When you're logged into Zoom, you have to have your camera pointed at where you're working, the computer, since you'll be taking it on Canvas, right? Pointed at your computer screen and so on and so forth while taking the exam. It will be proctored in that way. Those in person, it will be like any other exam in person and so on, right? The time limit for the exam will be, in all exams, will be 60 minutes, even though the class is 75 minutes or 85. Was it 80 minutes? I can't remember from when it starts. 80 minutes? Thank you. Yeah. Right. Class period's 80 minutes. Exam will just be 60 minutes, and that's because the university for finals, basically for a class like this, right, where we're supposed to alternate people coming in for the final exam, that will still be the case where we'll have to alternate, and half of you will take the exam like at the beginning of like the 3-hour window we have, and the other half will take the exam at the end of the 3-hour window that we have for those taking it in person. And so the exam has to be an hour, basically, in order to accommodate people coming in and out and changing out who's in and who's not here, right? So the final exam will only be an hour long. And so the regular exams, I'm also making only an hour long to be the same type of experience, okay? Right. And for those taking the exam, again, on Zoom or, you know, over Canvas, you get the same time limit as everyone else in the class, right, to submit your answers. There will be, so there's already example exams that I've given from previous semesters of teaching this class that you can look over. Answers are also available on Canvas already. You know, so there will be some kind of free response, right? So on those taking it online over Canvas, it will be typically numerical entry, and you'll have to enter some number. But in order to receive partial credit at the end of the exam, you'll have ability to upload a file, and so you can upload a hopefully scanned PDF document of what you have, right? And I suggest using the Adobe Scan app. So there's this Adobe Scan app they can use, and right, you hold it up over your document, wait a minute for it to adjust that out. Right now it's not working super quickly because I'm not really holding it over the entire page, right? But it'll try to figure out where the outline of the page is, right? You can change and crop it however you want, okay? And then click continue, and then it will keep on scanning pages as you keep on clicking continue. And then when you're done, you just click on the bottom right here over the file, and then you have your scanned files, and you can save as a PDF, right? And then once it's finished processing that, I can open it, I can share it via email, share a copy or something like that, right? So, right, and so the app makes it very easy to upload a PDF of your work, right? If you're not able to get it to work and have to open image, like take screenshots or pictures or something, then that is what it is. But yeah, so you will have the ability to upload your work on Canvas for those who are taking it online to get partial credit on free response questions. Okay. So yeah, and then otherwise, right, keep making sure that you're attending SI sessions, right, for the class. Okay. So any questions about any of the kind of announcements that I just went over, quizzes, exams, and so on, anything about course, about material we've covered, whatever. Any questions at all from those here or over Zoom? So for people who go to class on Monday, just don't worry about the participation for the week. There will, right, the people who come to class on Wednesday, right, you won't have a Wednesday class the week of Thanksgiving. So they're just, you know, it won't matter. So, right, so it'll work out that like half of the class is getting participation, you know, credit this week, and then another half on that other week. And so I'll just combine those 2 weeks into just 1 week, right, type of a thing. So for those who attend class regularly on Monday, don't worry about doing like these participation questions that right are handed out in class. So any other questions? Right, some of those for you who are here today, right, you won't have to worry about it for the week of Thanksgiving, right, since there won't be a Wednesday class set. All right. So if there are no questions, then we'll go ahead and get started. Finishing up chapter 13. Essentially, we'll do some more examples of concentrations and converting between concentration units and things of that nature. And then we'll also talk about colligative properties. Okay. So this first example here, which actually is not in the chapter 13 handout, is the one I recently added, right? In the problem here, it says, right, in water, roughly the fluoride concentration is 1 part per million. Okay. And question is, what is the concentration in units of molarity, right, for this water sample? Okay. Given that the density of water is 1 gram per milliliter, right? Here. Again, what I'll do is, for those online, let me create a breakout room. Right, so on those on Zoom, if you want to go to the breakout room after I open it, you're welcome to discuss the problem if you'd like. And then I'll close it when it's time for us to work over the problem together as a class. And those here in class, right, you're welcome to discuss with people in the class if you'd like to while working on the problem. Okay. Let me move that out of the way of the problem so those in class can actually see what the problem is. All right. So let's go over how we solve this problem. Okay. So as part of this, right, I'm writing out kind of the relevant kind of data, if you will, given in the problem, as well as some extra little things, right? We're told the solution is 1 parts per million. We're told the density is 1 gram per milliliter. Okay. I know, right? I mean, I'm standing next to a periodic table to help me out. Right? You'd be given a periodic table. You don't have to memorize molecular weights and things like that, right? I know the molecular weight or molar mass of fluorine in water is 19 and 18 grams per mole, respectively, right? And then I'm asked for what the molarity is, right? And the molarity, recall, right, is defined as what? All right, moles solute over liters solution, right? In our case, the solute is fluorine. Okay. Right, and so if we want to get that molarity, we need to figure out how many moles of solute I have in some number of liters of solution. Okay. So how would what would be kind of one of the first things I'd want to try to do to help solve this problem, this question? Right, yeah, I want to find the moles of fluorine. In order to find the moles of fluorine, I need to know, say, the mass of fluorine, right? And to make the problem kind of simpler to figure out these things, what should I do? What did we do on the last problem last week? I guess it was on Wednesday, right? Since we didn't meet Monday, right? One of the first things we did in the last problem last week, we converted between a bunch of stuff. We made an assumption. Right? So remember, right, when I'm converting between concentration units, right, the total amount of solution that I have does not really matter, right? Because a solution is defined as a homogeneous mixture. So if I have 10 liters, 5 liters, right, doesn't matter. The concentrations will be the same, okay? And so I need to assume, to make my life easier, I need to assume some amount of solution or some amount of solute, or some amount of solvent, right? I need to assume I have some amount of something, right? Otherwise, you could solve the problem without doing that, but it's a lot more annoying, a lot more tricky, and it's a lot easier if we just assume some total amount, okay? Right? And so, right, as in Zoom here, Donald suggests, right, we could assume 100 grams of solution, right? I think, right, last week, that's what we did. We assumed 100 grams of solution. Right here, so we're going to assume, right, we're going to make an assumption. So we're going to assume, right, in this case, I'm going to just do 1,000 grams of my solution, right? 1,000 grams of my solution, right, is 1,000 grams total, right? And so let's write out, right, parts per million. So 1 ppm, right, parts per million is what? What's parts per million defined as? Mass of solute over the mass of the solution times 10 to the 6 here, right? Times a million, right? And so if I assume, right, 1,000 grams of solution, right, plugging that into this problem, I have 1 equals the mass of my solute, which again, my solute is fluorine. And that's what we're trying to solve for, right? Right, because as was stated, right, we need to find the moles of fluorine. To get the moles of fluorine, I need to first find the mass. And then the masses of the solution, I've assumed, right? I just said, okay, let's say I have 1,000 grams of solution, right? And then that's times 10 to the 6, which is 1,000,000, right? Right, you simplify this, you get 1 equals the mass of fluorine times 1,000, right? Which tells us that the mass of fluorine equals to 0.01 grams. 0.1 or 0.001? Oh, sorry, 0.001 grams. Got an extra 0, right? Right, so that's the mass of fluorine, right? 0.001 grams. That's the mass I have in 1,000 grams of water, or of my solution, right? I got 1,000 grams of solution, 0.001 of those grams is fluorine, right? And I know that because the solution is 1 parts per million, okay? So now I can use my mass of fluorine to get my moles. How do I get from mass of fluorine to moles of fluorine? Yeah, we got to divide the mass by the molar mass, right? So I take 0.001 grams of fluorine, divide it by its molar mass of 19 grams per mole, right? That is going to give me 5.26 times 10 to the minus 5 moles of fluorine. Okay? So this is the moles of fluorine, right, which I need for my molarity, right? I need the moles of solute. And so the other bit for my molarity is I need the liters of solution. So what do I use to convert or get the liters of solution?
The density given.
What was that?
The 1 gram per milliliter that was given in the problem.
Yeah, so we want to use the density, right, and use the fact that we have 1,000 grams of solution, right, that we've assumed in this problem, right, and then I use my density here, the fact that's 1 gram per milliliter, right, to get the fact that my solution then is 1,000 milliliters or 1 liter, right? And so that's why I picked 1,000 grams, and so it comes out to be 1 liter, right? If I picked 100 grams of solution, it would be 0.1 liter, right? And in the end, I'd get the exact same answer, but it just, you know, makes numbers come out a little bit easier, okay? And so that is my volume of my solution, right? So I use that here, right? I use the 1 liter in my volume of solution, right? Liters of solution in the denominator. And then I use my moles of fluorine, right, as the moles of solute in the numerator, right? So the molarity, right, of fluorine, right, the concentration of fluorine in solution in terms of molarity is going to be 5.26 times 10 to the minus 5 divided by 1, right, or just 5.26 times 10 to the minus 5 molar, right? And so that is the molarity, right, of this solution. That's 1 parts per million. Okay? Again, you'll get that exact same concentration, that exact same molarity, no matter what total amount you assume. Okay, you can assume 1 gram, 1,000,000 grams, whatever you want to assume, you will get this exact same molarity in the end. Okay, and again, you can do the problem without making that assumption, but it makes things a lot more annoying. So, questions about this problem? Right, we do these example problems here in class. Right, we have the homework questions, we have the quizzes, right? All of these different examples, all these different questions are here to practice and prepare for exam questions, which will be essentially identical to these type of questions, right? This question, right, posted on this slide, right here, right, fluoride concentration in parts per million to molarity, right? That could easily be a question on an exam, okay? And so that, right, and so the exam questions are not going to be any different than the type of questions we do in class. So please make sure you ask whatever questions you have while we're doing these things in class, right? Attempt these problems, right, in class during the time I give you guys to kind of work on them yourselves, right? I may not give you enough time to finish it yourself, but at least attempt to get started. Think about how you would solve the problem, so that, you know, we can gain confidence when it comes time to take the exam to solve these problems on our own. Okay. Right. All right. So questions? Yeah. Yeah, so if you ever have a problem where it's not telling you the total amount of like solute and solvent there, it's just giving you like a concentration solution, then yeah, I would, like 99% of the time, you're going to need to assume some total amount to kind of solve the problem. Yeah. Right, we've had, now, right, like if there's a problem like this, right, where it tells you how many moles of solute I have, right, 0.1 moles of NaCl, and 8.6 moles of water, right? That tells me the amount of everything I have, so there's no assumptions I need to make, right? But, right, in this problem that we did last week and then the one today, right, you're just given like a mass percent, you know, some sort of concentration unit, and you're converting to another concentration unit, and yeah, you definitely want to just start off by assuming some total amount, okay? And you can pick whatever you want, right? Again, some assumptions make the math a little bit simpler, right, in terms of multiplications and divisions, but we could have assumed some total mass of fluorine. We could have assumed some total mass of the water. That would have been a lot more difficult, right? Right, but a lot of times the assumptions like I try to make with these type of problems is like the assumption is like here, where I'm given parts per million, and I know parts per million is mass of solute over mass of solution. So I typically assume some sort of mass of my solution so that I can just plug in a number to that denominator and get the mass of my solute, for example, right? Essentially do this part here, right? So I'll use this often to guide what my assumption is going to be. You know, whether it's a total mass of solution, or if you're given molarity, maybe I assume a total volume of solution, things like that. But yeah. Other questions? So actually, I don't have something on the slide, but I'll just ask the question. Let's make a new slide here. Get this. Should have added a slide on this, but didn't. What is an electrolyte? And yeah, I don't have those later. Oops, shoot, sorry. What is an electrolyte? Right. What's an electrolyte? What's a colligative property? We'll have some other questions we'll try to pop up here. Let me share this screen. Those on Zoom here. Yep. Right. So the first question is, what is an electrolyte? Yeah. So an electrolyte, right? An electrolyte is going to have to dissolve in water, right? So an electrolyte, right, dissolves I mean, typically we're talking about water, so water, right? You could say in solution, it could be a different solvent, but typically we're dealing with water, right? And what is an electrolyte? I mean, if either think of like what does an electrolyte do when it dissolves in water, or think of examples of electrolytes. Either one is fine. Yeah, so an electrolyte, right, dissolves in water and allows, or helps the solution conduct electricity. That's how it gets the name electrolyte. Because an electrolyte, when dissolved in water, right? And this is not the same thing as like Gatorade, like infused with electrolytes or something like that, right? That they're using electrolytes for whatever their own definition, right? But an electrolyte is a species that dissolves in water. When it does so, it helps that solution conduct electricity. Okay. Right? What would be an example of an electrolyte? Anyone had to take a guess?
Would salt be one?
Yeah, salt, right? Sodium chloride, right? Any other examples?
An acid?
An acid. Yeah, it depends on the acid, but yeah, like a strong acid like HCl would be an electrolyte. We'll talk about weak electrolytes when we talk about weak acids, but yeah, so like HCl, acid, okay. Now, what would these things, like when sodium chloride dissolves in water, right? What's actually in that water? Do I have just chunks of sodium chloride in the water or something else in the solution?
You've got sodium and chloride ions separately.
Yeah. Mm-hmm. And so an electrolyte, something that dissolves in water, right, helps to conduct electricity and breaks apart into ions when it dissolves, right? So electrolytes are things that will dissolve in a solution and create ions in those solutions, right, because they break apart, right? So for example, sodium chloride, right, that will break apart when you dissolve it into sodium ions. Plus chlorine ions, right? And hydrogen chloride would also say break apart in solution to hydrogen ions plus chlorine ions, right? Right. So those are examples of electrolytes, right? These are things that break apart in solution to form separate ions, okay? Right. And real quick, a non-electrolyte is just things that don't do this, right? So non-electrolyte is something that doesn't form ions in solution when it dissolves, right? Doesn't break apart, doesn't help the solution conduct electricity, okay? Right. Typically, your electrolytes are, ionic compounds and things like that, right? Doesn't have to just be like, metal with a non-metal, right? You could have like CO3 2 minus, right? So like another example, right, would be something like Na2 CO3, right? This would be an electrolyte because this will break apart an ion to sodium ions and carbonate ions, right? So right, and so it doesn't have to be like an acid or like a metal and a non-metal or something like that, right? It could be ammonium nitrates or something like that. Okay. Right. But there are things that break apart, dissolve in solution. Typically, they're ionic type compounds, right? And then, your non-electrolytes are going to be just typical kind of organic based compounds and other things like that, right? Things that just aren't going to break apart and form ions in solution. Okay. Right. And so what is, right, so the last part of this chapter, we're going to be talking about colligative properties. What is a colligative property? Either what's an example or how would you define a colligative property?
Like the boiling point and viscosity.
Yeah. So, right, boiling point elevation, right, is an example of a colligative property. Okay. And let's see, viscosity, close to something kind of related. So viscosity is mainly a property of the solvent, but vapor pressure of your solution is a colligative property. Any other examples, or anyone want to take a shot at how would you define a colligative property? Huh? Yeah, right. So freezing point depression, right? So right, the freezing point, because this is the most kind of common example, right? Right. So freezing point of something changes, right? When you add, right? Like trying to define it without giving an example here. I guess, I don't know. What's an example of like everyday life using this kind of freezing point depression, colligative property, changing the freezing point of something by
So
doing
adding antifreeze to your radiator.
Yeah, so antifreeze, right, which is a mixture of something and water, right, to change the freezing point of that water, right? Salt on a road, right, to melt the ice on that road, right? Right, and what you're doing is, right, you're adding a solute to something, right? Yeah, right. So a colligative property, right, is something that depends on the amount of solute in a solution, not the type of solute. Okay. Like the type meaning like whether it's, you know, whatever it is, right? Whether it's hydrogen, helium, sodium ions, chlorines, right? Doesn't matter. It's just the amount, how much stuff do I have in solution, right? And is a property of the solvent. Okay. Right. So colligative property. Where did that add title shoot? And just to blow things up, right? So colligative property, right? Something that depends on the amount of solute you add to the solution, right? And is some inherent kind of property of the solvent. Okay. So it's going to change some aspect of the solvent, right? The solvent has a boiling point, it has a vapor pressure, it has a freezing point, right? So those things, those properties of the solvent get changed by the addition of a solute, and it just matters on how much solute I add, not what is the solute, what is its interaction with the solvent, right? Just matters how much I add, essentially its concentration in that solution, okay? So questions about back. Right, so questions about kind of what we're talking about on this slide, right? Electrolytes are things, right, that dissolve in solution to form ions. Those ions help that solution conduct electricity, right? And a colligative property, right, something that depends on the amount of solute in a solution, right? Not that's what the solute is, and then is a property of the solvent. Right, and so how many ions do I get in solution when I dissolve NaCl? 2, right? Right, what about Na2CO3? How many ions am I going to get in solution? You get 3, right? I'm going to get 2 sodium ions and 1 carbonate ion in that solution, right? So do some more examples, right? How many species are formed in solution, right? How many ions are formed in solution, right? For these,
So with that sodium bicarb, would that be a weak electrolyte because it doesn't dissociate completely because there's still carbonate that didn't dissociate?
well, so it fully dissociates into sodium ions and carbonate ions. Carbonate itself is a molecular compound, and it will not break apart in solution. So yeah, so something fully dissociating doesn't mean it has to break apart into individual atoms. It just has to break apart into like, it has to break apart essentially ionic bonds, right? So sodium carbonate here, right, is, right, the sodium and the carbonate ions are ionically bound to each other. So those will break apart in the solution into separate ions, but carbonate or carbon-oxygen bonds are covalently bonded, and those aren't going to break apart in solution ever. Yeah.
Okay, thank you.
Mm-hmm. Other questions? All right. So then for these guys, right, think about how many species are formed in solution. So for the first one, C6H12O6, if I dissolve that in solution, how many species, how many things is it forming? How many different things? Yeah, just one, right? Because when you're dissolving something in solution, you're not going to break up covalent bonds, things like that. So C6H12O6 is just a covalent compound, an organic compound. That doesn't break apart in solution. That stays as a molecule itself, right? So it's just going to form one thing in solution itself, right? Sodium chloride, right, forms 2 things in solution, right? Talked about sodium ions and chlorine ions. Yeah, question? About, yeah, species. So, I mean, it's related, yeah, so comment here about Van Hoff factor. It just, how many unique things get formed in solution when you dissolve this thing in solution? So C6H12O6 forms only one unique particle in solution when it breaks apart, because it doesn't break apart. It's just C6H12O6, right? Sodium chloride, when you dissolve it in solution, forms sodium ions and chlorine ions, which are unique from each other, that are apart from each other in solution, right? Right, if I dissolve, what? Yeah. Right, so NaCl, right, so I'll put up what I'm writing here in a second, right? Let me move this here. Right, I have, sodium chloride solid. When I put that in solution, right, I can add water, right? Like dissolve it in solution. I get sodium ions and chlorine ions. These are 2 unique ions, 2 different things that get formed in solution. And so it actually doesn't have to be like different atoms, and we'll do the example of that in a second, right? But in solution, right, what happens, right, as I start off with this like NaCl, right, solid, chunk of NaCl, when I put that in solution, right, I get Na plus ions surrounded by some waters, right? And then I have chlorine ions that get surrounded by waters as well, right? And so, right, if I put just one of these molecules in solution, I put this one molecule in solution, I will get 2 things in that solution, right, for every one of these that I add. Okay? That makes sense, right? And so, right, and so that's forming 2 species in solution, 2 things in solution, right? So here, right, K2SO4, if I just take one K2SO4 molecule, how many things get formed in solution? 3, right? So in this case, I get, right, like if you think of like unique elements or something like that, right? I get potassium and sulfate, but I get 2 potassiums in solution, right? Right, because again, if you think about like what's happening in solution, if I take that K2SO4, right, pop that in solution, right, I'm not going to have potassium and potassium ions sitting next to, I'm not going to have like K2 plus or something like that, right? It's not going to be like K2 plus in solution, right? That's not going to happen. What you'll get is you'll get a potassium ion surrounded by some waters in solution, right? Another potassium ion surrounded by waters in solution, right? And then a sulfate ion, right, surrounded by water and 2 minus, right? Surrounded by waters in solution, right? So I'm going to have these ions, K plus, right? These 3 different ions that are going to form in solution, right? That are all surrounded by water, right? And aren't associated with each other, right? They're fully broken apart, right? In solution, right? So that if I say dissolve, right? If I dissolve 1 mole or 1 mole of this per 1 liter solution, right? What that means is I'm going to get 1 mole of this ion per liter of solution, 1 mole of this ion per liter solution, and 1 mole of this ion per liter of solution. So in total, I have 3 moles of stuff per liter in this solution, right? I get 1 mole of K plus 1 mole of K plus 1 mole of SO42 minus, right? I get 1 mole of each of those things in solution if I dissolve 1 mole of I said H2SO4, sorry. K2SO4, right? Okay. And this is and this will be relevant to colligative properties, as we'll talk about in a second, right? But I get these individual mole, right, these things break apart into 3 unique ions in solution, and each one of those ions itself has a concentration of, say, like 1 mole per liter if I started off with 1 mole per liter of this, right? And I can look at that as well from the balanced chemical reaction of K2SO4 solid going to 2K plus SO4 2 minus, aqueous in solution, right? Actually, let me write this on a new sheet of paper so it's not kind of crunched in everywhere, right? So this is solid going to 2K plus aqueous, right, plus SO4 2 minus aqueous, right? And so if I dissolve 1 mole of this in a solution, right, what will happen when it dissolves in solution, I get 2 moles of potassium ions and 1 mole of sulfate ions, right? So I get a total of 3 moles of stuff, right? 3 moles of different things, 3 moles of stuff, right? So this one thing breaks apart into 3 things, okay? And so that's right. That's what this question is asking, right? That's what we're trying to get at, right? How many things does it break apart into when it's dissolved in solution? Okay. So 3 for K2SO4. What about AgNO3? 2, right? That will break apart into 2 things in solution: Ag plus, NO3 minus, and then finally NH43, PO4. That will break apart into 4 things in solution, right? It will break apart into 3 NH4 pluses plus 1 PO4 3 minus. Oh. Right, so this, let me share the screen, right? So we get 1, 2, 3, 2, 4. Right. Yeah. That's where we were. Right. And so that's the number of species, right? The number of things that are formed in solution when these things dissolve in solution, right? How many things do they break apart? Right, and so answering these questions, looking at the colligative properties and things like that, right, will be important to remember what are our, like, identifying ionic compounds, right? What are things like nitrate, sulfate, carbonate, phosphate, right? Those type of ions, right? Polyatomic ions, right? Kind of identifying those things. Again, you don't have to identify like the name sulfate is SO42 minus versus sulfite or hypersulfate or hypochlorite, or you don't have to identify the formula with the names. I don't care. I'm not going to test you on that. But right, if you see these compounds, right, we do need to be able to identify how many things these would break apart into solution, right? To do that, you have to identify, oh, this is an ionic compound, and this will form 2 potassium ions and 1 sulfate ion. Okay. Yeah.
So you for that so long as it's a polyatomic ion, it won't dissolve in solution, but I guess it won't break apart in solution.
Yeah. So like a polyatomic ion like NO3 minus, right, doesn't break apart in solution, right? You're never going to dissolve something in solution and it's going to break apart covalent bonds. Okay. You can break apart ionic bonds when you dissolve things in solution, but never covalent. Okay. Any other questions about? All right. Right, so we talked about we actually mentioned the 3 examples of colligative properties that we have: boiling point elevation, vapor pressure, and freezing point depression. Thank you. Right. Right, and so, right, the question is as the concentration of the solute in a solution is increased, the boiling point will blank and the vapor pressure will blank. Will the boiling point increase or decrease, and will the vapor pressure increase or decrease? All right, you got some people on Zoom here saying B, right? Okay, and it is in fact B, right? So the boiling point elevation, I think I forgot to put the other slide here. Yeah, so the vapor pressure changes, but I guess kind of the name of how it changes is often referred to as vapor pressure compression, or I forget that's the exact name that used, but like, right, the vapor pressure depression, like the vapor pressure goes down with addition of a solute, the freezing point goes down with the addition of the solute, and the boiling point goes up with the addition of a solute. Here, the boiling point will increase and the vapor pressure will decrease, right? With the addition of a solute. Okay. Questions about this? Right, so we should remember those general trends about boiling point, vapor pressure, and freezing point, right? The boiling point goes up, vapor pressure and freezing point go down when you add more solute. All right, so this question is referring to the Van't-Hoff factor. That Van't-Hoff factor is what we solved for in this slide here, okay? So the Van't-Hoff factor is, right, there's a technical definition of what it is, We won't really focus or worry about that in this class. It's talked about in the lecture videos online. But for the sake and purposes of this class, right, the Van Hoff factor is how many species does this thing form when it dissolves in solution, okay? And so this slide, right, resets the questions is, right, this slide is asking not how many species are formed in solution, but it's also asking what is the Van Hoff factor of these compounds, okay, right? And so when you think Van Hoff factor, think how many species does this thing form in solution, okay? Right? And so for this question, right, what is the value of the Van Hoff factor for AlNO3,3? Okay. The exact same question for this is how many species are formed in solution? How many things get formed when this breaks apart in solution, right? This meaning AlNO3,3. So on Zoom, right, a number of people are saying C4, and that is correct, right? I will form one aluminum ion plus 3 nitrate ions, so I'll form 4 different things in solution. So its Van Hoff factor is equal to 4, okay? That Van Hoff factor, I don't have the equations here, but they are actually in the handout. So in the, say, equations that are given on, say, quizzes and exams, right? The boiling point, elevation, and oh, they don't have the Van Hoff factor written in these equations. Shoot. All right, scratch that. I was going to use that as a reference, but I'll just write it out, right? So the change in our freezing point temperature and change in the boiling point temperature are given by the exact same set of equations, right? It's going to be this Van Hoff factor times some constant, talk about those in a second, times molality, okay? So I here is your Van Hoff factor, okay? KB, KF, these are your boiling point, elevation, constant, right, and your freezing point, elevation constant. Right, and then M is the molality of your compound. Right, molality is moles per kilogram solvent, okay? Right. Right, and so these, right, are the equations that determine how much the freezing point decreases and how much the boiling point increases, right, with the addition of some amount of solute. Okay. Right, again, those are in the lecture notes as well, with, you know, these things detailed and written out and discussed on the videos on the lecture slides. So let's do an example here on calculating the boiling point and freezing point of a solution that's made by 100 grams of ethylene glycol, right, in 4,450 grams of water. Okay. So this is essentially what your antifreeze is a mixture of water and ethylene glycol. Okay. Now, typically you do these mixtures by volume ratios, right? Typically it's 50% water, 50% ethylene glycol, right? But water is more dense than ethylene glycol, and so that's why it ends up being more of a mass, right? That's why it's 4,000 grams versus, say, 1,000 grams. But these gram ratios are relatively equivalent to the volume ratios that you typically use in antifreeze. So I'm just going to swap over here, right, because the question's also written out. This example problem. All right, so let's write out the relevant equations here. Right, the freezing and boiling point changes. Okay. Right, and so we're asked essentially to find, right, the boiling points and freezing points, right? So these delta T's in these equations, right, is what we're asked to find. We're given KF and KB, right? Ethylene glycol is just C2H6O2. It's an organic compound, so what is its Van Hoff factor going to equal?
1.
1, right? It's not going to break apart into anything else in solution. So I is just equal to 1. And so the main question is what is the molality, right? The molality, molality, yeah. Molality, right, is defined as over kilograms of solvent. So we need moles solute over kilograms of solvent. That's a K, I promise. Right, and so the kilograms of solvent, right, we are given that in the problem, right, that's 4.45 kilograms, right? 4,450 grams converted to kilograms is 4.45 kilograms, right? And so how do I get the moles of my solute, which is what, C2H6O2, right? That's our solute. So how do I get those moles? Yeah, so we're going to take the 1,000 grams of C2H6O2 and we're going to divide it by its molecular weight, which is 62.07 grams per mole. Okay. Again, you would have access, you'd either be given that molar mass, right, in the problem, or you're going to be given a periodic table where you can easily calculate it, right? And so when we do that, we get 16.11 moles, right, of this. And so the molality M is just going to be 16.11 divided by 4.45, okay, because that's the moles of our solute, right? And then the mass of our solvent in kilograms, okay? And so that just comes out to equal 3.62 molar. Questions so far? Yeah. Yeah. KF, KV, those would always be given. You do not need to memorize those whatsoever. Those would always be given. Yeah. Yeah.
I don't know if I mentioned this wrong, but I know that on the posted lecture, it's a little bit chapter was the value of the electrolyte divided by the non-electrolyte.
Yeah, so the technical definition is you measure the colligative property change of the electrolyte solution and you divide that by how much colligative property should change by the non-electrolyte solution, and that would give you the actual Van Hoff factor. In this class, we're just concerned about the theoretical Van Hoff factor, which is assuming 100% dissociation. So the actual value is the fact that like sodium chloride will not necessarily 100% dissociate, maybe like 95% dissociate or something like that, right? And so in that case, the Van Hoff factor would be, instead of 2, it'd be like 1.9 or something, right? But again, we're only going to deal with whole numbers and things like that in this class. But yeah, so the technical definition is as you described it and as it is in the lecture notes. We're just worried about kind of the theoretical value, which is, how many species does this break apart solution, assuming 100% dissociation. Okay. Other questions? All right. So now to get the changes in freezing point and boiling point, right, we just do delta TF equals I KFM. So I is equal to 1. KF is given as 1.86. And the molality is 3.62. So the freezing point changes by 6.73 degrees Celsius. Okay. Right, the regular freezing point of water is 0 degrees Celsius, right? So the new freezing point, right, testing what are the boiling points and freezing points, so not what are the changes, right? But my new freezing point is going to be minus 6.73 degrees Celsius. Okay, right? And so that is the new freezing point of this mixture of ethylene glycol with water, right, to make antifreeze. And that's why it's antifreeze, right? Because it lowers the freezing point by over 6 degrees Celsius, okay? Right? So it makes it so that that liquid freezes at a much lower temperature, right? It makes it much more difficult to freeze. Because if it were to freeze, right, if you used just pure water in your engine, right, in the coolant system in your engine, and it got significantly below freezing point and all that water froze, right, you'd break your car, right? Because that water, when it freezes, expands, and it's going to expand and break something when it does so. Yep.
Will it always be resistant to water, like material and boiling?
If it's not, if the solvent is something besides water and it's asked what is the new freezing point or boiling point, you'd be given like it boils at this temperature or it freezes at this temperature. So you know like what to take the difference of. If it's water, it's assumed that you know that it freezes at 0 Celsius and boils at 100 degrees Celsius. But yeah, otherwise if it's some other solvent, you would be given that information.
So when it freezes, you could subtract it from the freezing, and with the boiling, you also subtract it.
You add it, right? Because remember, freezing point depression, so the freezing you subtract, right? Boiling point elevation, boiling you add, right? And so to get the boiling point change, it's just that 1. Now the boiling point constant is 0.52, and then 3.62. So the new boiling point is, right, the change is 1.9 degrees Celsius. So the new boiling point is 101.9 degrees Celsius. Okay. See, there's a couple questions here on, wait, why is I equal to 1? Yeah, so I is Van Hoff factor, and it equals 1 because, yeah, that compound doesn't dissociate. Thank you to those students who helped answer that question. But yeah, so the answers from those students' class are correct. So why is the freezing point negative? Because so the new freezing point is the old freezing point. I'll call it like new, right? Is the old freezing point minus the change in the freezing point, right? Because the freezing point is decreasing with the addition of a solute, okay? And my old freezing point is 0 degrees Celsius, right? This is 0 degrees Celsius. So I take 0 minus my change, which gives me negative 6.73, right? The new boiling point of my water is the original boiling point of 100 degrees Celsius plus the change, which is 1.19, right? And so again, we subtract the change for freezing and add the change for boiling, right? And for water, our freezing point is 0 degrees Celsius, boiling it's 100. Uh-huh. Yeah, I mean, yeah, I mean, yeah, the concentration, right, starts at 0 if there's no solute, and it only gets to a higher number the more and more solute you add. Yeah. Mm-hmm. All right. Other questions about this problem?
I have a question. It's not really necessarily related to the problem, but so this problem deals with 1,000 grams of the ethylene glycol to 4,450 grams of water.
Yep.
would the boiling point and the freezing point change if you added 2,000 grams to the same amount of water?
Yes, it would be double the change, right? If I doubled the amount of solute, I'm going to double the change because it's kind of this linear relationship between the concentration and the freezing point. So if I did 2,000 grams of ethylene glycol, I would get a new freezing point of minus 12 or 13.46 degrees Celsius and a new boiling point of roughly 104 degrees Celsius. So
Okay,
you double these changes if you double the amount of your solute. Okay.
cool. Thank you.
Mm-hmm. Right, and that's and again, it's because it's a colligative property, right? It just depends on the total amount of solute you dissolved in your solution, right? So I double the amount of solute, I double the change. Okay. Other questions? Right. So here, right, you have a question, right? If I prepare a solution where I take, say, 1 molal of this, 1 molal of that, right, 1 molal of each of these guys, right, to make a solution, right? Which of these solutions will have the lowest boiling point? Yeah, so it is going to be B, right? So the boiling point, right? Again, think boiling point elevation, right? So the more stuff I add, the higher my boiling point is going to be, right? Well, each of these compounds, I added 1 molal of them, right? But not all of these compounds break apart into the same number of stuff, right? They have the same Van Hoff factor, right? And so the smallest Van Hoff factor will end up having the lowest boiling point because they'll have the smallest change, right? So B here, this has a Van Hoff factor of 1, A has a Van Hoff factor of 3, C has 2, and D is 4, right? And so the boiling point, the lowest will be for B, then C, then A, and then D. D will have the highest boiling point because the more stuff I add, the higher increase my boiling point is, right? And so, yeah. So in this case, this question is just comparing Van Hoff factors because they all have the exact same concentration rate for each of these species in solution. Okay. Oh, thought I had another question on here, right? If I didn't have the same concentrations of all of these things, right, you need to compare the Van Hoff factor times the concentration of that compound, right, to figure out what gave you the highest or lowest boiling point. So how does D have a Van Hoff factor of 4, right? So D, when you dissolve it in solution, will form 3 different potassium ions plus 1 phosphate ion. And so that will give you 4 different ions in solution. And so that's going to give you 4 species in solution and have a Van Hoff factor then of 4. Okay. Other questions? Right. So they're online. There is a solution to this last kind of problem here. The fun little thing, right? You have 1.22 grams of a solid suspected of being pure cocaine, right? You dissolve that in 15.6 grams of benzene, and you measure the freezing point lowering by 1.32 degrees Celsius. Right? We want to know what is the molar mass of that solid, right? And determine whether or not that molar mass agrees with the molar mass of, say, cocaine, right? And to do that, we use the fact that that change in temperature is related with IKFM, right? And we're given delta T, I, assuming it's a molecular compound, right, is equal to 1, right, for a molecular compound. KF is given, right? And so I can calculate M, the molality, and then from the molality, I can use the mass of my solvent to get the mass of my or the moles of my compound, and I'm given how many grams I had in my compound to then get the molecular weight, so or the molar mass. So if you have kind of questions about this question, I'm happy to go over it in more detail. But like, as I said near the beginning of the semester, I'm going to try to end the class at least a number of minutes early so people don't feel rushed to exit the room. So I will only go over this if people want to stick around and go over it, or people on Zoom want me to go over it real quick, I can in more detail. But otherwise, I will see you guys on Monday. Okay. Right, for those here in class, please drop off your participation questions on the table before you leave. Okay. Say that again? Yeah, sure. I can go over this. So I'll start kind of just going over it now, right? So again, what I want to find is the molar mass, right? Which is the moles of my compound, I'll call it X, over, or sorry, the grams of X, my apologies, right? The grams of X over the moles of X, right? I'm told in the problem the mass of X that I have, but I don't know how many moles is in that mass, right? And I use this information, right, the rest of the information in the problem to find the number of moles, right? Because I know that the freezing point change is 1.32 degrees Celsius, right? The Van Hoff factor, I'm going to just say is 1, because again, if I'm suspecting this of being cocaine, then I'm going to suspect it's a molecular compound, right? And so it's going to have a Van Hoff factor of 1, right? Kf is 5.12, okay? And then the molality, I do not know, but we can solve for it, right? So I take 1.32 divided by 5.12, okay? And shoot, I didn't have that number prepared. Do that real quick. 1.22 divided by 5.12. So that gives me a molality of 0.258 molals, right? Which is equal to the moles of my solute, right? My unknown compound X, right? Over the mass of my solvent, right? The kilograms solvent. Well, I know the mass of my solvent. It was 15.6 grams, okay? So 0.258 molal is equal to X moles of my solute over, now I got to convert this grams to kilograms, and so that ends up, when you do that, you convert it, you'll get 0.0156 kilograms of my solute. And so now just multiply 0.0156 over, and you get that the moles of your compound X equals 0.00402 moles. So now finally I have the moles of my compound, I'm given the mass, and so now I can plug that in to solve for the molar mass, right? I can get that molar mass is equal to 1.22 grams divided by 0.00402 moles. Okay, so 1.22 divided by 0.00402. That gives me a molar mass. Did not really write out things very well. Okay, so that gives us a molar mass of 303.4 grams per mole. Okay, and if you were to look up the molecular formula of cocaine, you'd find that that would be this, basically the same as the molar mass of cocaine, right? Which isn't definitive saying that it is cocaine, because you know lots of things can have that molar mass, but it would help verify that it might be. Okay. So yeah, so I ran through that kind of quick, but if you have questions, yeah, 303.4. Sorry, that is a 4 grams per mole.
Thank you so much.
Yep. Yep. Yeah. So right, when using this equation, delta T F equals I KFM, delta T is just like the absolute value of what it's lowered by, right? Technically, right, the freezing point decrease, right? So there's like a negative temperature change, right? But when using that equation, we're just caring about like what is the magnitude of that change, right? And then when we want to calculate the new freezing point, then we want to use the fact that that change is negative, right? So I take my old freezing point and subtract off the change. Okay. But yeah, for the sake of this equation, you just always use a positive number for that temperature change. Yep. All right. Any other questions? All right. No questions here over Zoom, then I will close out the meeting.